Welcome. In this lesson, we will be learning about measures of shape. A measure of shape is a statistical or mathematical value that is used to describe the geometric properties or structure of a distribution. Now, it can also be defined as a numerical descriptor that is used to give a summary on the shape, size, or orientation of an object. Now, that being said, we'll move on to quadratic functions. Now, a quadratic function can actually have the coefficient of x squared to be positive. Okay, so in the quadratic function, the coefficient of x squared can be positive or negative. Now, if it is positive, the curve opens upward, like you can see here. But when it is negative, when the coefficient of x squared is negative, then it opens downward, just as you can see there. All right, now if we decide to plot this distribution, we are going to have the curve opening upward, just like you can see here. So we'll just substitute the values of x, and then we'll get a corresponding value for y, or we get corresponding values for y. Okay, then we go on. But in the case of a normal distribution, if you open what we have here, what we have here is actually this. What we have here is this. So when you open it, you have this. So you can see that it is actually a quadratic function. So, but this time around, because it is, okay, so we are saying e raised to the power of all of what you can see here. So it's going to have a shape that looks like this. All right, and this is actually the distribution function of a of a variable that follows a normal distribution. So this is the distribution function or a normal distribution. Okay, so when it is represented mathematically. So we go on. Now let's look at symmetry of distributions. A symmetric distribution is one which has equal tails to the left and right. Now, an example of a symmetric distribution is a normal distribution. Now, there are other symmetric distributions, but the normal distribution is one that has a bell shape, and it is, just as we said before, it is symmetric, but its shape looks like this. Now, it's not just having a bell shape, but it has a particular formula which we call its probability function. So, which is actually this, what you see here. Now, it's bell shape, and it is symmetrical because if you divide it by maybe a line at the middle here, then it will actually be, so what will be left in the left part, or what you have in the left part, will be equal to what you have in the right part. Now, a distribution that is not symmetric is said to be skewed or asymmetric. All right, so if the distribution, now looking at this, actually a normal distribution looks something like this without these things that are here. But what I'm putting here in green is actually, or what I have put here in green is actually to show you something. Now, this part will be called the left tail, while this part will be called the right tail. Now, looking at this, coming back to the left, coming back to the skewed distribution, now you will have the left tail and the right tail. But in the symmetric distribution, the first one called left skewed distribution, or left skewed distribution or negatively skewed distribution, is actually a distribution that has a longer tail to the left. So the left tail is longer than the right tail, but that's not so with, that's not so in your normal distribution. So when you come back here, Now, the right skewed distribution has a longer tail to the right. So, and so the tail, okay, it has a longer tail to the right. The right tail is longer than the left tail. And we also refer to this as a positively skewed distribution. So now, when it is not symmetric, it is said to be skewed. Some people may prefer to write the word asymmetrical, but I'll be using asymmetric here. Okay, now, all right, so your positively skewed distribution is, okay, or we define the positively skewed distribution to be one that has a longer tail to the right, and we define a negatively skewed distribution to be one that has a longer tail to the left. All right, so that is that about that. Now, there are times when we may not be able to decide if a distribution is skewed to the left or to the right by just looking at what has been, maybe by just looking at data set or looking at even a curve that is plotted. So it is always a good practice to obtain a coefficient of skewness. So if we obtain the coefficient of skewness, if we are going to obtain it, we can use any of the formulas that we have here, depending on whether our data is from the population, I mean, it's coming from the entire population, or it is coming from a sample taken from the population. Now, if we have the data that we have been given here, just 1, 2, and 3, we can obtain the mean to be 2. The standard deviation will be, okay, the variance will be 1 and the standard deviation will be 1. Now, going by what we have obtained, we know that this is our first observation. So we say 1, going by the formula, 1 minus the mean. The mean is 2. Then we'll go to the next one. 2 here. 2 minus the mean. The mean is 2, don't forget. So 2 minus the mean. And finally, the third observation, 3, which happens to be this, minus the mean. The mean is 2. So when we do that, we are going to cube everything. That means raise each one to the power of 3. To the power of 3, which is what we see in our formula. And then when we do that, this will give us minus 1 raised to the power of 3, and that will be minus 1. 0 raised to the power of 3, 0. Minus 1 raised to the power, okay, this one will be positive 1 raised to the power of 3, and that will give us positive 1 still. And when we add everything, we get 0 divided by 2. So how do we get the numerator here? N is 3, so 3 minus 1. So n minus 1 will be 3 minus 1. And s is actually, you can see it from here, is 1. So s raised to the power of 3 will be 1. So 1 times 2, that gives us 2. Okay, so you eventually get a coefficient of skewness of 0. Now, so this is how to interpret the coefficient of skewness. A positive coefficient of skewness means that the distribution is skewed to the right. A negative coefficient of skewness means that the distribution is skewed to the left. A coefficient of skewness close to 0 implies that the distribution is approximately symmetric, and a coefficient of skewness that equals 0 implies that the distribution is perfectly symmetric. So if we look at our data, the one we just obtained the skewness coefficient for, it had a skewness coefficient of 0, and so that means that the distribution is perfectly symmetric. All right. Now let's look at how we can determine the extent to which a distribution is skewed. Now let's assume that the distribution is positively skewed. Then in that case, the higher the value of the coefficient of skewness, then the more positively skewed the distribution is. For instance, a distribution that has a skewness of +2 is more positively skewed than a distribution that has a skewness of +1.5. So that means this distribution having a coefficient of skewness of +2 is more positively skewed than the one that has a skewness of +1.5. So take note of that. Now, assuming that the distribution is negatively skewed, then the lower the value, the more negatively skewed the distribution. For instance, a distribution that has a coefficient of skewness of -3 is more negatively skewed than one with a skewness of -2. So please take note of that. So these are the uses of skewness. All right, so we can move on. You can pause it to see them well if you want to write them down. All right, so we move on to kurtosis. Now, statistically, kurtosis is a measure of the peakedness or tailedness of a distribution. Okay. Now, geometrically, kurtosis is a measure of how pointy or how flat a distribution is. Now, if you just want to describe the distribution, then we may say descriptively, kurtosis is a measure of the extent to which a distribution is small, less outlier prone than a normal distribution. Meaning that okay, so it's likely to have, we want to see how likely it is to have outliers, how likely it is to have outliers when we compare it to a normal distribution. So that's what we want to see there. Okay, so now going by the first definition, we said kurtosis is a measure of the peakedness or tailedness of a distribution. So somebody may say peakedness, but actually peakedness or tailedness of a distribution. So peakedness, so the peak and the tail. Okay, so let's go on. Peakedness. So peak, the highest point of the curve. Okay, and the tail, I've talked about tails the other time. Now, so a leptokurtic distribution actually has a higher peak and heavier tails. It has heavier tails than those of a normal distribution. So, all right. So, the tails. Now, a platykurtic distribution has a lower peak and lighter tails than those of a normal distribution. So you can see the labels. All right. So yeah, as I said, a platykurtic distribution has a lower peak and lighter tails than those of a normal distribution. All right. So then a mesokurtic distribution actually has a peak and tails that are very close to those of the normal distribution. Now, let's go on. So, let's define now. In order to talk about the kurtic distributions, or rather to be able to determine which kurtic distribution we are talking about, we need a base mark. That base mark can be 0 or 3. So if you are using a base mark of 3, then you say a distribution is kurtic, is leptokurtic. For instance, let's start. If you are using a base mark of 3, it will be leptokurtic when the coefficient of kurtosis is actually greater than 3. Whereas you are going to say it is mesokurtic when the coefficient of kurtosis is 3. And you are going to say it is platykurtic when the coefficient of kurtosis is actually less than 3. Nonetheless, you may decide to use 0 as the base mark. So if you use 0 as the base mark, it will be leptokurtic when the coefficient of kurtosis is greater than 0, mesokurtic when it is equal to 0, and platykurtic when it is less than 0. Okay. All right. So that's it. So if you're using, but if you want to use a base mark of 0, then you need to change the formula a little bit. So in that case, let's talk about the coefficient of kurtosis. Now the coefficient of kurtosis is defined like this. So if you're using, this is for the population, this is for the sample. So if you're using this one, then your base mark must be 3. So here, your base mark must be 3. So please take note of that. However, if you are using this base mark of 0, then you can use the formula by the left. So please take note of that. Now, but I will be particular about this one. So the one by the left. If you are using a base mark of 0, you use the one by the right. But if you are using a base mark of 3, you use the formula or formulas by the left. Okay. Now, let's go on. Assuming we are using a base mark of 3, then the kurtosis formula will actually be what you have here. So just look at the similarity between skewness and kurtosis. Now this one is your variance. So let me indicate that to avoid confusion. Sample variance. Okay, but we'll come back there. Now looking at this, x minus mu the same. For kurtosis is 4, for skewness is 3. For kurtosis, sigma is raised to the power of 4. For skewness, sigma is raised to the power of 3. In the sample, the difference is that you don't use n, you use, or the differences are, number 1, you don't use n, you use n minus 1. You don't have sigma, you have s, but both are still raised to the power of 4. And the same thing applies, or similarly, it applies to your skewness. And so when you come to that of the variance, sample variance, okay. Now the sample variance happens to be this one. And you notice that you are raising x minus x bar, or x minus mu to the power of 2. Okay, but you divide by n minus 1 in the case of the sample variance, which is this. But in the case of the population variance, which is this, you divide by n. All right, so those are the similarities. We'll move on. Now, using the data that we had before, let's assume that, okay, we are trying to obtain the coefficient of kurtosis now. If we want to obtain the coefficient of kurtosis, then we are going to have, okay, if we calculate x bar, it's going to be 2, n is 3, the number of observations. Then we have our variance to be 1 and our standard deviation to be 1. And then when we then when we begin to put all these values into our formula, then we're going to have what we have here. So how do we do that? We have 1, 2, 3. Okay, that's our data. Okay, 1, 2, 3. Then we have the variance to be 1 and the mean to be 2, and the number of observations. The number of observations is actually 3. And so what we do, first observation minus the mean. So 1 minus 2, the mean is 2. So second observation, 2 minus 2. So 2 minus the mean is 2. Then the third observation, 3 here, minus the mean is 2. So each one will be raised to the power of 4, and we're going to have what we have below. Eventually we have a kurtosis of or a coefficient of kurtosis of 1. All right. So how do we interpret this? Going by that, we return to how we interpret the kurtosis thing. So we are using a base mark of 3 in this case, and that is going to be, okay, so what we have is less than 3, so that means the data has fewer extreme values and the distribution has a relatively flat or broad shape with lighter tails compared to a normal distribution. So this the distribution that we just looked at is actually platychotic. So let's go back, and according to our data, okay, so according to what we obtained, it has a kurtosis or a coefficient of kurtosis of 1. So the coefficient is 1, and that means that it is platychotic. Well, a distribution can actually be symmetric, and yet it is not normal. So please take note of that. All right, so in this case, the distribution that we had, which is 1, 2, 3, that we used in our example, actually is symmetric and platychotic. Please, the word platychotic should actually be Y there. Symmetric and platychotic. So symmetric and platychotic. So that's it about this one. Some other distributions may be symmetric and leptochotic, maybe symmetric and mesochotic. It may even be skewed and leptochotic, and other combinations like that. So if you are using a base mark of 0, coming from the formula I showed earlier on, this formula, no, not this. Sorry. Yes, this formula. Okay, coming from the formula the formulas by the right, then you will have to use this interpretation. So that being said, we have come to the end of this lesson. Thank you.